Hello, Mr. Claudia here, and today we are going to begin our final chapter in IB Math SL, and that is the trigonometry chapter. Now this is a big chapter. I've kind of used it as a catch-all for everything related to trigonometry. So we're going to start by looking at geometry and shapes and angles of triangles, but then by the end of this chapter we're going to be looking at trig functions and the derivatives and integrals of those trig functions. Now, trigonometry is the study of triangles. And it really, all of trigonometry comes back to this basic idea of similar triangles. If you have two triangles that have the same angles, then the relationship or the ratio between side lengths is the same. So for example, these two triangles have the same three angles. So the relationship or the ratio of length AB to DE is the same as the ratio of, say, BC to EF. This can be extended to all sorts of applications and all sorts of, we can look at all sorts of different ratios between triangles, but we're most interested in right-angled triangles and the relationship between different sides. The ratios that we use the most often, we actually have given special names. So for a right-angled triangle, we'll define an angle, a non-90 degree angle, and then the sides in relation to that angle, while the adjacent side across from that angle is the opposite side, and then the longest side of the triangle, called the hypotenuse, we mark with an H, I guess. The most frequent ratios that we use are sine, which is the ratio of the opposite over hypotenuse. Cos is adjacent over hypotenuse. Tan is opposite over adjacent. You would probably remember this as SOHCAHTOA, a really short form of remembering the ratios. Because remember, similar triangles mean the ratios are always the same. Even if I have a really big triangle versus a really small triangle, if the angles are the same, then the ratios are the same. So you can imagine back in the day before we had these things in our calculator, there were big tables at the back of textbooks where you would look up these common ratios. Now you probably learned in a previous math course about the reciprocal trig functions. So 1 over sine, which is cosecant, 1 over cos with secant, etc. These are not in IB Math SL, so you don't have to worry about these for our course. Okay, the next thing we can talk about is figuring out what the angles are, or what these ratios are. Now, luckily, your calculator can do these things for you. Making sure that you're in degree mode, because today we're talking about degrees, you can find what sine 45 is by typing it into your calculator. And I get sine is equal to 0.707. I'm writing it to 3 significant figures. This is called an approximate answer. Which means basically that you used a calculator. And you had to round it. So it's approximate. It's not ideal from a math perspective. But if you have a calculator exam, this would be an acceptable answer. It's rounded to 3 sig figs. However, you also have to be aware of how to do this using, if you had a paper 1, you didn't have access to a calculator. It's expected that you've memorized a few key trig ratios. And these trig ratios, we remember them often by using these two triangles. The first triangle, we call these the special triangles. This first triangle, I call it the 1, 1, root 2 triangle. It's a neat one to, it's an easy one to draw. Basically what you can do is draw a triangle where the non-hypotenuse sides are 1. So you go 1, 1. This now means that it's an isosceles triangle, which means that because these two sides are the same, these two angles are the same. If this is 90 degrees, then these two angles have to also add up to 90 degrees, because remember the sum of all the angles inside of a triangle is 180. So this is going to be 45 and 45. Now, how do I know what this hypotenuse is? Well, I can use the Pythagorean theorem, right? You remember a squared plus b squared equals c squared. So 1 squared plus 1 squared is equal to c squared. So that's how you end up with c is equal to the square root of root 2. 2 is equal to c squared. So there's a reasoning to be able to draw this triangle pretty quickly. All you have to remember is 1, 1. From this triangle, you can figure out any ratio involving 45 degrees. So for example, if I ask you for sine 45, let's start here. I need my sine, remember, is opposite over hypotenuse. So I have opposite is 1 and the hypotenuse is root 2. So my answer is going to be 1 over root 2. And that would be an exact answer that you would use on a paper 1. And that is you use special triangles. It is expected that you know these triangles. These are now in IB. Don't worry about rationalizing the denominator. You don't have to, at least for my course, and IB won't dock you if you have a square root in the denominator. Okay, cos 60. Similarly, I can find an approximate answer by typing this into my calculator. Oh my god, it's 0.5. How neat. But if I want an exact answer, I can use the other special triangle. I call this and this is great, the 1, 2, 3, or the 1, 2, root 3 triangle. To remember how to draw this, all you have to remember is an equilateral triangle where all 3 sides are 2. If all 3 sides are 2 and then you draw a line down, or an altitude or a line down the center to split the triangle in half, then each of these bottom sides are going to be length of 1. So that's how you have the 1, 2, and then similarly I can use Pythagorean theorem to find that this is root 3. So 1, 2, 3, half of 2, 2, and 3. Similarly, if it's the equilateral triangle, each of these angles is 60 degrees. So now if I split it in half, this becomes 30 degrees. So now I have all the ratios I need for a 30 degree or a 60 degree angle. So if someone asks you what a cos 60 is, well, cos is adjacent over hypotenuse, so it ends up being 0.5. Okay, so those are the triangles. Hopefully you can remember them, you know how to sketch them. They're not on your formula sheet, but again, my strategy is to draw an isosceles triangle with 1 and 1, and here is to draw an equilateral triangle with all 3 sides 2. Okay. Let's go, before we get to some problems, let's go over some other common things that we talk about when we're looking at trigonometry. And these are some crucial definitions. Angle of elevation, angle of depression. So if you're looking out at the horizon, we call that a horizontal line. And then if you have to tilt your eyes slightly up to look at, like say, an airplane, that angle between the horizontal, the flat line, and where you're looking, that's your angle of elevation. If you can imagine, it's like you're taking the binoculars, you're looking straight, and then the angle, you're pointing them up. Similarly, if you look below the horizon line, that would be the angle of depression. That's if you're looking down at something. Another term we use that you might not have seen in the previous course is bearing. This does come up in IB. It's part of the curriculum. Bearing comes from using a compass to navigate, orienteering. For bearing, or if you're driving a boat, I guess, or driving a plane. Bearing, when we talk about bearing, you would give a number between 0 and 360. Right, because there's 360 degrees in a circle. 0 is always north. And then you turn like a clock and go all the way to angle 360 degrees. So if someone says I have a bearing of 241 degrees, well, that means that you're 90, 180, you're somewhere going southwest-ish. If you're at an angle of 10 degrees, you'd be going almost north, right, up here. And if you had an angle of 350, you'd be going just kind of northwest a little bit. And then there's compass directions, and this is the one I think you've probably seen if you've studied physics. You can have an angle like north 40 degrees east. When I read this, the first direction tells me which direction to go. Then the second number and letter tell me how far to move in which direction. So 40. This one is saying go north and then 40 degrees east. So turn slightly, so you have 40 degrees east. Or conversely, you could write the same thing as go east and then go 60 degrees north. And that'll give you the same angle. I have another one here. You go south, 15 degrees west, or you could go west, 75 degrees south. So those are all ways of measuring angles in different situations. And those can all come up in an IB question. So I know this is a lot of review. I've tried to give you questions that are more challenging here, or that will kind of help you realize if you need to do some more work. And maybe questions that you haven't seen before. So a hiker walks north for 5 kilometers. She then turns and walks another 3 kilometers on a bearing of 107. Oh, so this could be tricky, especially if you have not done a a bearing question before. So our hiker walks 5 kilometers north. Then she turns and walks another 3 kilometers on a bearing of 107. Okay, so what is 107? Let me draw like a little compass rose here to try to figure it out. So north, remember that was 0 degrees. This was 90 degrees. This down here would be 180 degrees, sorry, 180 degrees. She went 107, so she actually went just a little bit more than 90. So I'm gonna draw somewhere like that, that's my sketch. And she only went 3 kilometers this way, so it's not actually as far. Probably didn't draw the best thing there. So she went up, then she went down. How far is she from her starting point? So really the question is, how far has she traveled? Or how far is the distance as the crow flies from her starting point? So let's call that x. Okay, well this I could, okay, well I can't really solve anything. I mean, first thing I need to know is, yeah, it's not a right angle triangle, so I can't use SOHCAHTOA. Actually, there are no SOHCAHTOA questions in my review, but you could do some practice ones in your, for homework. So what can I do here? Well, I would need to know some more information. I would need to know an angle. For example, do I know this angle? Let's call it theta. Not really. However, I know that this whole angle, let's call this angle alpha, and I know that this whole angle is 107 degrees. So actually I could figure out what theta is, right? I could say theta is equal to, well, this whole thing would be 180 degrees minus 107. So that gives me an angle of 73. So now I have a side angle side. Hopefully this is jogging some memories for a contained angle and 2 sides. That's what we might call SAS. We use the cosine rule, or the cosine law, depending on how you're taught it. Okay, so this is actually on your formula sheet. If you go to the geometry and trigonometry section in your formula sheet, you have the sine law, you have the cosine rule. Sorry, sine rule, cosine rule. So you don't have SOHCAHTOA, but you do have this here. It doesn't really explain it to you, so you have to remember how to use it. So I'm going to find x squared. That's going to be 5 squared plus 3 squared minus 2 times 5 times 3 cos 73. Now I'm going to sub in those, use my calculator to do this calculation. So I have 5 squared plus 3 squared minus 2 times 5 times 3 times cos 73. So my answer is, well, it's x squared. My answer for x squared is 25.2288. I take the square root of that, and I get an x value of 5.02 kilometers. Does that number make sense? She walked 5, but then came back a bunch, so her total walking was 5 kilometers. So that is an example of a bearing question, and actually an example of a cosine rule question, which maybe we should have talked about first. So the SOHCAHTOA formulas are used to look at a right angle triangle, but you have these 2 rules as well, sine rule and cosine rule, that can be used to solve any triangle, even ones that are not right angles. Sine rule tells you, the relationship between this angle and this length is equal to this angle, and sine of this angle and this length is equal to sine of this angle over this length. So there's a sine rule. You could write it upside down too, it's exactly the same. The cosine rule, as we just talked about, it almost is a modification of the Pythagorean theorem. A squared is equal to b squared plus c squared minus 2 times bc cos a. So really, if you're trying, like we were trying to do, is find an unknown length, you kind of have to orient the cosine rule appropriately, choose the appropriate layout. So if I'm trying to find, say, a, for example, then you have to actually know what cos a is, what the opposite angle is. If you want to know, if you're trying to solve for b, again, you need to know the opposite angle. So you kind of reorient the cosine rule as necessary. The times when you use these, so if just going off of here, for cosine rule, we use it for situations where we know three sides or where we know side angle side, a contained angle. The sine rule, on the other hand, we use if we know angle angle side or side side angle. But side side angle is the one where we have to be careful, because this is where we can have a situation. We can have something called the ambiguous case. And I know you hated studying this when you did, but this is in the IB curriculum. The ambiguous case for the sine rule comes about because sine is positive in both the first and second quadrant. And the situation you have to be able to recognize is when you have, or when it will occur, is when you have side-side angle. So when you have an uncontained angle. So here, for example, I know I have a length of 10, a length of 16, and an angle of 30. And if this outside side is the shorter one, then you can have this kind of situation where, well, the length of 10 could be here, or it could be here. You could have an acute angle, acute triangle, or an obtuse triangle. This angle here can either be acute or obtuse, and again, that's because sine can be positive or negative, is positive in both cases. So if you're not sure when this is going to occur, you look for side-side angle. You look for this kind of flapping side that could flap either way. If I knew this length, and if this was a contained angle, I wouldn't have this problem, because this is actually the bottom length is the length that changes, right? Here it's very short, here it's very long. And there I gave you my explanation. So this is something to be aware of. If you're unfamiliar with this or you don't like it, I've highlighted on the front a whole bunch of homework for today, and there are some ambiguous case questions. Okay, let's move on. Sometimes you get questions that combine different multiple steps for trig. So for example, a surveying team are trying to find the height of a hill. They take a site on the top of the hill and find the angle of elevation to be 23. So I'll just draw a little picture here. Hopefully I can draw a nice picture. This is actually a real life kind of thing. This is how people, when you see those people at the side of the road measuring like the angle of the road, they're in those kind of vests and they're taking these measurements with those the sticks and the sight. They're actually trying to figure out the angle of elevation of things. So they have some sort of hill, right? This is the thing we're trying to figure out. The height of the hill, let's call it x. And okay, I take a site on the top of the hill and find the elevation to be 23. So if you can imagine this angle is 23. They then move a distance. Okay, so we don't know how far away they are from the hill. And we know this is a right angle triangle though. But we can't solve it because we only know an angle, we don't know any lengths. They then move a distance of 250 meters on level ground directly away from the hill and take a second site. From this angle, from this point, the angle of elevation, so the angle above horizontal, is 19. So that's here. And we know that this length is 250, that they walked 250 away. You can imagine a person doing this, right? They took their measurement to the top of the mountain. We don't know how far they are from the mountain, but then they take 250 meters back, they take another measurement. Now, can we solve this question? We want to find the height of the hill. Well, if we could find this length, then for this first triangle, we would have a length and we'd have an angle. We'd be able to find the unknown length using trig ratios. But first up, we need to find what this length is. Now, can I do that? This second triangle here is not right angled, so I can use either sine rule or cosine rule. I know what this angle is. I know what this length is. Do I know this length? No. Do I know this length? No. Can I figure out what this angle is? Oh, absolutely, I can. Let's call this angle alpha. So angle alpha is going to be 180 degrees minus 23. That's what we did before. We know this whole thing is 180 minus 23. That gives me 157 degrees. We call that complementary angles. The two angles add up to 180 degrees. Okay, now I know that I know what this angle is, so now I have angle, side, angle. In this case, oh, I'm still not really there yet, but I can figure out what this angle is as well, because now I know what two of the angles are, so I can figure out what beta is. Beta is equal to, okay, well, all three of these angles add up to 180. So 180 minus 19 minus 157. 180 minus 157 minus 19. That gives me a very small angle of 4 degrees. So what we just did there is that was the sum of triangle angles. Okay, so now we have angle, angle, side. Right? So angle, angle, side. Oh, I can use my sine rule. So I have sine. Okay, so sine 4 degrees over the opposite length, which is 250, is equal to, okay, I want this length, so I need the opposite angle, so that's sine 19. And let's call that, no, let's call it y. Now I don't have a lot of space here, but we're going to cross multiply, and you can do the math, so it would be sine 19 times 250 divided by sine 4. Make sure you're in degree mode, because everything we're doing today is in degree mode. I end up with y is equal to 1166.8. That would be the sine rule. If you're going to round, which you're probably going to round, make sure you keep more digits around than 3, because you shouldn't round until the very end. So now that I know what y is, and I have this right angle triangle, this angle, with respect to this angle, this is the hypotenuse, this is the opposite. So which ratio involves opposite and hypotenuse? That would be sine. So now I would write sine 23 degrees is equal to my opposite, which is x, over my hypotenuse, which is 1166.8. Again, I'm pretty small solutions here. Hopefully you can take more space. But I basically multiply this, multiply this number times sine 23. That gives me a final answer of x is equal to 455.906 equals approximately 456 meters. Cool, and our surveyor, that guy at the side of the road with that surveyor stick, just figured out the height of the mountain, or whatever it is, the hill. Cool. So that's an example of a kind of two-step question you can get with trig. You've probably done things like this before, but maybe you've forgotten. Again, there's some practice in your homework. Now, the one thing you probably have never seen, we really don't teach it in the regular grade, regular high school, Ontario high school curriculum, is the formula for area of a triangle. We can develop this formula. I'll show you quickly how it's developed. If I take any triangle in the world and I drop this altitude line, or this height of the triangle, I'm going to call that height. Okay, remember height, well, for this right angle triangle, so I could use right angle triangle to express this using my angle here, angle B. So with respect to angle B, this is the opposite, and the hypotenuse is C, is this other length of my triangle. So it would be sine B is equal to H over C. If I cross multiply, I get an expression for the height. Now remember, the area of a triangle, which you learned a long time ago, was half, area is equal to half times base times height. So I have half, in this case my base is A, my height is, oh, I have a formula for height. Here it is, C sine B. So I end up with this formula, half AC sine B. That's a really neat shortcut for finding the area of a triangle. And it's actually in my formula sheet in case you forget. This is new for us. It's something you're not familiar with. Let me show you what's cool about it. Is that if I want to find now the area of this triangle, I don't have to figure out the height. I just take half times the base times one other length times the angle between those two sides. Similarly, if I don't know this side but I know side B, it would be half AB sine C. So it's pretty powerful, and it's really impressive how quick you can solve questions now. This is where you're going to need to spend your time for today's lesson, because you haven't ever seen questions like this before. It's an easy enough formula, but it can be tricky to apply it. For example, let's say I have a regular pentagonal garden plot. So a pentagon means you have 5 sides. Regular means all sides same length. It's like a perfect pentagon, you could think. It has a center of symmetry 0 or O and a area of 338. Find the distance OA. Oh, sorry, this is point O in the middle. That's like the center of my pentagon. And this is A, so I'm trying to find this length here. Well, what we can do is see that this is, the area is 338. So each of these mini triangles is 1/5 of this area. So we could say that the area of each triangle inside the pentagon is 338 divided by 5. So that gives me 67.6 meters squared. So now if you want to kind of zoom in on this, one of these triangles, we have a little kind of wedge like this. This is length, this is O and A, and this is technically A2, right? They're both the same length. So it's an isosceles triangle. And can we figure out this angle here? The interior angle for each triangle. Well, this would be 360 degrees all the way around. So your angle for one of these triangles is 360 degrees, again divided by 5, which is 72 degrees. So now I know that this is 72 degrees. So now look at what I have. I have the area of this, right, 67.6. I have the angle, and these two sides are exactly the same. So I can use the area formula. Area is equal to half OA times OA times sine alpha. Remember what we talked about? Side times divided by times half times sine of the angle in between. Now you can sub in some numbers, right? I know that this is 67.6. This is half, technically OA squared, sine 72. Again, I don't have a lot of room to show all my steps, but I'm going to take 67.6. Oops, let's see so you can try to see it. 67.6 times 2 divided by sine 72. That gives me OA squared is equal to 142.1577. Take the square root of that, and I get OA is equal to approximately 11.9 meters. This is a tricky question. Again, it's not the easiest example of using the area formula, but I want to kind of scare you into thinking, oh, I gotta spend some time on learning this. So like I said at the beginning, your homework, I've listed a lot of different homework you can do depending on how comfortable you feel with the topic. I would definitely recommend to do page 390, number 1 to 6, and 372, number 5 to 11. That is area of a triangle stuff and also some more difficult problems. And then depending on how you're feeling, or if you're shaky with any of these concepts, I've told you kind of which concept, what questions you could do to target those concepts. So good luck remembering all that trig stuff, and we'll see you next time.